So I'm going to kind of take this in a direction that not every zoology class does. Because yeah, we've gone through the taxonomy, we'll be doing more evolution, and that's going to give us an idea of who we're talking about, how we can keep track of things. But what I want you to think about is form and function. How do these things actually work? So we're going to look at actually function today and how organisms have to function in the real world because, you know, that's where they are. The resources in the universe, on our planet, and in each of the individual ecosystems that we're going to be dealing with. So we need to look at that. And the other thing I want to show you is that the conditions we see inside the animals, inside living systems, are really quite different than they are in the environment in general. We'll see they're much more ordered. There's a subset of what's possibly there. And it's very, very different, and organisms have rather elaborate systems to make sure that that's the case. So let me give you kind of a big overall, this is what I want you to take away from this with. All right, evolutionary change produces systems that maintain homeostasis within organisms and regulate the distribution and allocation of resources, leading to a better ability to capture and process resources that lead to more offspring being produced. Evolution makes reproduction more successful. Now, I'll let you write that. Kind of a lot of verbiage, a lot of words, and kind of a larger statement. I really can boil that down into a much smaller statement. Basically, that. All biology boils down to is sex and food. Do is take a look at some of the systems that kind of help you not die off. And then from there, I'm going to have you do another simulation. So the examples I'm giving you, I put in those packets, so you've got them, so you can pay attention to me instead of writing. And so we'll just kind of go through these. Most of these shouldn't come as any great surprise to you because, I mean, you're an animal, you've been through school this far, you know what most of these systems are. I just want to make sure that you get it down to where you totally understand, and whenever we start talking about a new group, that's what you see. Okay, so I want to start with overall symmetry. Now remember, we're going through this, and I'm actually going to have you come up with an organism that matches a scenario that I have given you that you have not looked at yet, if you did what I said. Okay, so animals come in a number of different symmetries. First is asymmetrical, meaning that there is no, you can't cut the critter in half any way and get two even halves. Okay? We have radial, so things like sea anemones, sea stars, where they're basically built on a circular plane. There's no anterior, there's no posterior, and there's normally no head. Last but not least, the one you're probably the most familiar with is bilateral, because that's what we are. And you can run a plane right down the middle, and then what you have that are essentially the same. Okay? All right, I'm going to give you a list of what the different homeostatic systems are. Your book handles them slightly differently than you probably were originally taught, and I think this is a much better way of doing it. Kind of takes us a little bit more back to first principles, not quite so vertebrate-centric. So, the first is going to be, and I'm going to go through each of these. The first is protection, support, and movement. The second, communications, nervous. The third, communications, chemical. Gas exchange. No, I'm not saying the word respiration. Respiration implies vertebrate lungs, so we don't use that. Nutrition and digestion, temperature and fluid regulation, reproduction, and development. Okay, so now what I'm going to do is we'll go through each of these. I'll give you a set of what the main functions are. In some cases, because again, you're going to need to be looking at these. So, as I said, simple diffusion, body surface, none. An open circulatory system is what I'm showing you up here with this clam. Now, when we say open, we mean that the circulating fluid does not remain inside a vessel for its entire path. Doesn't mean it's never in a vessel, because for instance in this clam here, it has a heart, and it has vessels, but it also has a big open space in its foot here where the blood pools and then it's pulled out. It's a lower pressure system. We'll see later on why that makes a difference. And I want to contrast that to a closed. Now closed is what you have. It's also what squid have. And what a closed system is that you always have the circulating fluid in some sort of a vessel. The heart, all the heart really is a really big vessel. That's it. But you've got capillaries on each end, and the circulating fluid is always inside some sort of a vessel. Okay? Higher pressure system. Okay, now for the next, let's see, let's have you take 10 to 15 minutes because I'm going to want you each to explain what you do to everybody. Give ourselves 5 or 10 minutes at the end to do that. All right, here is where you guys get to decide what your animal should be. So, as a team, you find a new species. Don't use a real animal. I want you to come up with something that is not real, where you are building it. In the habitat assigned to you, describe and draw what you expect it to look like. What are its general characteristics? What are the challenges it faces to maintain an internal environment within range? Be sure your description covers all of the major systems of homeostasis as they relate to your habitat assigned, which is, that is. So each of you are going to have a different one. And I've given you some of the characteristics I want to make sure that you discuss. Basically, how much water is there, salts, elements and compounds, what are the gas levels like, what's the temperature like, what's the pH like, and how easy it is to find food. So, start talking.
Yeah, I would say something.
Go crazy, run wild.
It's protection, supporting movement. Okay. I feel like it obviously needs muscles, and a skeleton, probably an endoskeleton.
I agree with that. Kind of feels like if it has wings, just because it's already in the mountains, you know,
Be able to fly.
So we did more of a bird-like format, but it is not. It has quills on its wings, which it can then raise up for defense or to attract a mate. It is a plump little thing because it needs to hibernate, and it burrows instead of does a lot of flying. It does have weaker legs. It can only fly short distances, mainly used for getting around the mountain, so it doesn't have to rely